Dear students, I welcome you all. Today's topic of interest is characterization of compounds, especially with nuclear magnetic resonance spectroscopy. As you are aware that the structure of the compound plays a vital role for the reactivity, and most of the inventions were revolved around the characterization of the compounds. And let us see in this session how one can characterize organic compounds, especially with the nuclear magnetic resonance spectroscopy. Before entering the topic, I would like to summarize classification of nuclei. So, nuclei of most of the compounds can be carbon or oxygen or sulfur or nitrogen, whatnot, everything. I would like to remind you that carbon C612, which is having a atomic number 6 and atomic weight 12, oxygen atomic number 8 and atomic weight 16, whereas the sulfur nuclei, which bears the mass number of 32 and charge number 16, all belongs to one category with respect to one parameter, what we call spin quantum number I. Spin quantum number I for this nuclei is equals to 0. When spin quantum number I is equals to 0, all these nuclei are said to be magnetically inactive. Magnetically inactive means one cannot observe the NMR spectroscopic behavior of these nuclei. Though these nuclei are present in abundance in nature, one cannot take these nuclei to characterize the compounds. Another category of the nuclei belongs to, for example, proton, where its mass number is 1 and charge number is 1, carbon isotope 13, which bears the mass number 13 and charge number 6, and one more nuclei of most interesting is nitrogen 7 and 15, why not phosphorus, which is also bears an odd mass number of 31 and charge number 15. With these nuclei will bear nuclear spin quantum number I value will be given by 2Ni plus 1. I mean to say 2n plus 1 by 2, where n is equals to any integral values. For example, proton, in this case, n value is equals to 0. Therefore, its resultant I value will be off. Similarly, the nitrogen, which is having a value of n value is equals to 2, it bears, therefore I value becomes 5 by 2. And similarly, if one knows n number value for any particular nuclei, for such a nuclei one can guess very easily spin quantum number I value. Once spin quantum number I value is not equals to 0, such a nuclei are said to be magnetically active. What is the meaning of this one? Magnetically active means such a nuclei can be exposed to the external magnetic field where you can observe the NMR behavior. The NMR behavior of proton is more important because almost all organic compounds are expected to have proton in the as a constitution. And one more kind of nuclei that is present, nitrogen 714 and deuterium, which is the isotope of hydrogen, it will have spin quantum number I value is equals to n, where n is equals to integral value. So any value that can be given for this nuclei and etc. And when you are having a total view of a classification of a nuclei, one is in a position, everyone should be in a position to guess which nuclei can be subjected for NMR spectroscopy. Now, dear students, you are all aware that proton, carbon 13, nitrogen 15, phosphorus 31 can be used to find out what is the NMR spectroscopic behavior. Now, let me take this opportunity also to bring about the angular momentum and magnetic moment mu of the nuclei. Once a nuclei is said to have a resultant spin quantum number I, all these nuclei are expected to possess a resultant angular momentum P. Angular momentum of P is a vector quantity, a characteristic property of every nuclei is expected to exhibit. This angular momentum P is having a vector properties, and therefore it should have moment, it should have magnitude number 1 and number 2 orientation. The orientation preference or space quantization, what we call technically. Suppose if you know what is the I value for any particular nuclei, you can input this I value in the formula which is shown in the clipping. that is angular momentum P is equals to square root of I into I plus 1 into h by 2 pi units. If I is known to you, immediately substitute this one in this equation and one can calculate what is the resultant angular momentum. Similarly, the number of orientations or the number of directions or the space quantization of vector P, it can be given by the formula 2I plus 1, where I value is the spin quantum number I. If you know the resultant I value for any particular nuclei, immediately one can in position to calculate what is the resultant orientations or the permissible orientations or the space quantization values for any particular nuclei. As an exercise, students, I would like to suggest for proton, everybody try to calculate what is the angular momentum and how many number of orientations are possible. I am sure you will work out with this formula, because a proton is having spin quantum number I value is equals to half. Therefore, if you substitute half in the above formula, everyone can calculate the angular momentum value is square root of 3 divided by 4 pi into h units, where h is the Max Planck constant, number one. And number of orientations will be given by 2I plus 1, therefore I is equals to half, therefore number of orientations is 2. So therefore I believe every student by this time you are expertised in calculating what is the number of momentums and what is the number of orientations for a particular nuclei. Therefore, students, now I believe you are expertised in calculating the angular momentum as well as the number of orientations. We have seen the classification of nuclei based upon spin quantum number I value, number one. And number two observation what we have made is to be how to calculate angular momentum P with the help of the given formula. And as a third point, we are also expertised now to calculate the number of orientations permissible for a particular nuclei. The angular momentum vector P, which is a resultant angular momentum for any particular electron which is moving or a spinning body in a particular plane, it will be controlled by the angle of a plane. For example, in the above clipping, I would like to show you that angular momentum vector P can be positive or can be negative. When it will be positive, when it will be negative, let us see. In the above clipping, I would like to bring P is a positive in the first chart, because the motion of the electron or the motion of the body or the plane of the motion of the body is with reference to the reference framework such that its resultant P vector is in the positive y-axis direction. Whereas in the second clipping of the same chart, one can see the plane of motion. The plane of motion of the body has been inclined with respect to the reference framework, where the resultant P is now looking in a different direction. Still, it is positive in character. The third clipping, one can see the arrow mark, that is the green arrow mark which represents the resultant P vector. It is looking in the negative direction with reference to the reference framework, because the plane of motion of the electron has been totally tilted to the opposite direction. And finally, in the fourth clipping, see, one can observe the angular momentum vector P is totally negative, because the plane of motion of the body has been totally reversed when compared with the first clipping, etc. So therefore, even though the P vector is looking at different directions, it can have a different resultant values with positive character or negative character. I would like to remind you, my students, one important point in this junction: change of P vector orientation with change in the inclination of motion of the plane. But in all these cases, body has the same motion, that is in the same direction. The motion of the body direction is not changed, but the plane of motion is changed. Now we will try to look and try to understand what is the consequence of angular momentum vector P. Once a nuclei is having angular momentum vector P, the consequence of it is nothing but it will have magnetic moment. Magnetic moment mu for a particular nuclei, for which resultant spin quantum number I is known, can be calculated by one more formula, what is being called mu is equals to gamma into P, where gamma is called gyromagnetic ratio. Gyromagnetic ratio is the characteristic feature of a nuclei for which I value is not equals to 0. For example, in the same chart, one can observe Proton, for example, which is having a 1 and 1 mass number, charge number, will have a gamma value of 26.6 units, whereas the same parameters for your carbon 13 nuclei, it will be 6.06. Students, no wonder, because the gamma factor is also having a characteristic values of a positive and also negative. The negative value for a particular nuclei, if you want to know, it is the better example of nitrogen, else than what? The nitrogen is having a 15 mass number, it possesses a gamma value, that is gyromagnetic ratio value is minus 2.6. Now, gyromagnetic ratio, which is the characteristic feature of your nuclei, is nothing but it is the ratio of magnetic moment to angular momentum. So, therefore, the definition goes for gyromagnetic ratio is gyromagnetic ratio of a nuclei is defined as the ratio of magnetic moment to angular momentum vector. Once magnetic moment is there, what is the ultimate result? What is the ultimate consequence? What is the importance of it? Why we are so much concerned about the magnetic moment? Once a nuclei is having a magnetic moment, it is being influenced excellently by the external magnetic field. A nuclei for which angular momentum vector is there, it will have magnetic moment. Once magnetic moment is there, it will be influenced very greatly by means of your external magnetic field. So, if external magnetic field is given to the system, what will happen? And in the absence of external magnetic field, what is the structure or what is the orientations of these magnetic moments? It is very quite interesting, is it not? Now you come down to the clipping in the same chart. You can see all the nuclei. If you take 1 mole of a hydrogen gas or 1 mole of say HCl, in that HCl all the protons will randomly orient. Random orientation is possible because there is no external force that is necessary or force is acting on them to orderly arrange. So therefore, the orientation of protons in the absence of magnetic field is just like what I am showing in this clipping. So every magnetic moment need not follow any order. So random presentation will be there. This randomly oriented protons will be brought into the orderly orientation form with the help of external magnetic field. Just to right hand side, if you see, the protons have been subjected by the external magnetic field, where some of the magnetic moment vectors are aligned with the main magnetic field, whereas some of the protons will be aligned such that their magnetic moment is against. So any proton's magnetic moment vector, if it is aligned with the main magnetic field, we can say it is less energetic position. Supposed to be any nuclei for which its angular momentum, thereby its magnetic moment is aligned against to the magnetic field, then it is being called high energy position. So therefore, students, expose of magnetic field, giving of magnetic field, the influence of magnetic field makes the system to arrange in 2 different states. One is called alpha state, another one is to be beta state. We have seen the motion of body, though it is the same in all the cases, how its p vector can be positive and negative, number 1. And in the second point, what we have seen is to be, we had seen how to calculate what is a gamma value, and in the third point we have seen how magnetic field will brings the interaction. Through its interaction, it has orderly arranged the randomly oriented magnetic moment vectors and etc. And in essence, I would like to remind you one more important point, that 2 energy states have been created for the nuclei by means of external magnetic field. Now the question remains is to be, what is the energy of hydrogen proton which has been kept in the external magnetic field? So there is a possibility of calculating its energy by the following equation. The energy of a nucleus in any external magnetic field is given by E is equals to minus mu z H0, whereas mu z is called magnetic moment vector which is operating along the z axis, and H0 is the magnetic field strength. once magnetic field strength is known to you and magnetic moment vector is known to you, immediately one can be in a position to calculate what is the energy that is permitted or what is the energy that is being enjoyed by the nuclei in the external magnetic field. My dear students, at this point I would like to bring one more important point to your consideration, that is a magnetic spin quantum number. Magnetic spin quantum number m is also a parameter which is going to operate, which is going to influence the energy of the nucleus. So therefore the energy of the proton is being contributed by means of magnetic moment vector number 1 and external magnetic field number 2, and number 3 is the magnetic quantum number. Magnetic quantum number m can be having a values of plus of or minus of. So in plus of state, the nuclei will have a energy which is totally different from that of the nuclei which is there in minus of state. And one more important point, the two energy levels, once it is being created by the external magnetic field, one can calculate what is the energy of a nuclei which is present in m is equals to plus of state. This energy is branded as E1 and which is equivalent to minus gamma h by 2 pi into H0. Similarly, the energy of a nuclei which is supposed to be enjoying m is equals to minus of is branded as E2 and its energy is being calculated as gamma h by 2 pi into H0. So therefore, two energy levels of same quantities have been created and the energy difference between these two can be calculated very easily. Subtraction of lower energy level from the higher energy level will give you what is energy difference. This energy difference I have calculated and I would like to bring through the clipping of a third chart. In the third chart you can observe at the lowest part of this chart gives this idea. So one energy level E is equals to minus of, another energy level E is equals to plus of is created, and the energy difference between these two is calculated as delta E, which is equals to h nu, where h is equals to Planck's constant and nu is the frequency of the energy separation, is also again equivalent to gamma h by 2 pi into H0. Or from the same equation you can guess another important point, that this energy difference is also represented by means of a frequency which is nothing but frequency is directly proportional to H0. So therefore, depending upon the external magnetic field strength, the energy levels will be created and the energy levels will be separated, and these are also shown by the another representation extremely right hand side of this chart. Therefore, my dear students, once if you expose magnetic field, two energy states have been created and some molecules are occupying the lowest energy levels and some molecules are occupying the highest energy levels. Just to come down to the right hand side of the clipping, you can see four molecules, four protons are occupying the low energy state, whereas two protons are occupying the higher energy states. Under these conditions, suppose if you supply energy, that too which is belongs to radio frequency range, if you supply, the energy absorption will take place and thereby one of the proton which is present in the lower energy state, it will be excited to the higher energy state, and thereby this kind of excitation is called transition. A nucleus is showing a transition from low energy state to the high energy states. Once the supply of RF signal is cut off, automatically the reversal situation will take place. That is, the excited state will be loses and the nuclei which has been promoted from lower energy state to the higher energy state will come back and occupy the low energy states. In this event, when a molecule is supposed to be doing this kind of transition, what energy has been taken by the system, that will be released by the system. The released energy is picked up by means of the computer systems, computer networks, and which has been given in the form of chart. And finally, you would have a chart, just like imagine an ECG chart. In the ECG chart, various signals will be there which can be traced out by the doctor. Is it not? Like that, for a chemical substance also, you will get a chart finally. Through this chart, various signals you can identify, a chemist can identify, a chemistry student can identify, and finally he will tell how many protons are there in the system, what has been taken, and how many protons, where they are situating, and at what value they are supposed to be, and what kind of other parameters which is corresponding to these systems, and etc. Therefore, My dear students, I believe that I have given enough information regarding with the NMR spectroscopy, regarding with these fundamentals as well as the mathematical implications, and also I would like to bring the instrument finally. So when you comes to the instrumental part of NMR, we are having large magnitudes of magnets. These magnetic power of these magnets can be controlled by means of electronically monitoring systems, and thereby you can create any amount of magnetic field you want, and RF signal has been provided by its generator to the system, and this RF system supplies energy to the chemical system, and thereby chemical compounds or protons or the ingredients present in the system absorbs the energy and shows a transition, and when the transition is over, when the system reversal itself, automatically energy release will take place. This energy will be picked up by means of electronic media, electronic network, and thereby a visual communication will be given to you, and from this chart one can identify what is the structure of compound. NMR spectroscopy is the technique which is meant for the characterization of organic compounds. In this characterization, mostly protons were considered, and therefore the total technique sometimes goes as a PMR spectroscopy. This spectroscopy reveals not only the number of protons but also the position of protons, etc. The instrument which is going to be used for this spectroscopy is called NMR spectrophotometer, which is available in almost all advanced laboratories, and the principles behind this NMR spectroscopy is already revealed to you. Therefore I believe you are now how to use NMR spectrophotometer, how to take the NMR spectrum of a particular compound, and also how to analyze it.